start now, and if our technician committee technicians could share this possibility to share your screen.
Yeah.
Okay, thank you. So please start.
Is that okay? Can you see that okay, Oksana?
Yeah, that's great. Thank you.
Perfect. So thanks very much for that nice introduction. So as Oksana said, I'm going to be talking about the downstream impacts of retreating glaciers on water security, both from a water quantity angle, but largely today from a water quality angle. Thanks very much to Sergey and the organising committee for the invitation to talk today. It's really nice to be able to contribute. So a bit about who I am. First, I started life studying geography and environmental science in Scotland, and then went on to do a PhD in glaciology, and that's very much the field that I've continued to work in. I've spent time in Vancouver in Canada. I was a postdoc in Stockholm University in Sweden for 4 years, and more recently I've been based back in the UK as an associate professor at the University of Plymouth. So there's 3 parts to the talk I'm going to give today. The first part provides an introduction to glaciers as freshwater resources. The second will focus, this is probably the sort of large part of the talk, will focus on contaminants in the cryosphere and the impact they have on water quality. And in part 3, I'll just briefly introduce another project that I started working on in the last couple of years that's much more focused around the water, food, energy security nexus and the impact that glaciers have on that. So we'll start off with talking about glaciers as a freshwater resource first. And apologies if you know a lot of this already, but I know that we might have a fairly broad audience here today. So a bit about water security then. What is it? Essentially, water security is access to drinking water and sanitation, and it's a key component of that nexus, those 3 things that we need to know about, which are central to sustainable development and also to livelihoods as well. And as we know, there are pressures from lots of different areas, pressures on food due to growing population, land use practices that can impact on that food production and thus things like water resources too, and economic growth. And all of that produces a huge amount of pressure on that nexus. But I would argue that water is probably the most exploited of the natural resources, and about 70% of the extraction of water can be attributed directly to agriculture, to food production. So it's very much a circle of dependency on these different natural resources. In addition to food production and water security challenges, there's also land degradation caused by different land use practices. I saw in the talk before, we're talking about gully erosion, and obviously there are impacts of land use practices on that, and downstream impacts in terms of water and sediment transport too. And if we think about energy consumption as well, about 30% of global energy consumption is also attributable to food production and supply. So water security is inextricably linked with all of these other components of the security nexus. So coming on to glaciers then, what do they contribute? Glaciers, ice caps and ice sheets, so the main land ice bodies in the world, cover about 10% of the Earth's surface. But despite that being quite a small percentage, they actually contain about 70% of the total fresh water globally. So a huge amount, and much more than we see in our lakes and rivers. So they are very much a store of fresh water that are really integral to people downstream. And that's particularly important in areas such as the Himalayas and the Andes, where literally hundreds of millions of people are directly reliant on fresh water from glaciers upstream. For sometimes just part of the year if there's a dry season, but sometimes for much longer periods of the year as well. And in these regions, in places like the South American Andes, glacier contribution, not just to drinking water, but also to irrigation and energy in particular, is becoming increasingly important as we move forward. But as I'm going to talk about in this talk as well, in addition to water quantity and how much is available to support the nexus, the quality of that water is also crucial. And I would include things like the sediment load, as well as anthropogenic and natural contaminants in that talk about quality as well. So this slide just tries to show quite how reliant some parts of the world are on glacial meltwater. On the right side of the screen, the concentric circles which show Bolivia, Peru, Chile and Argentina. The largest circles on the outside, the lighter colour, this corresponds to hectares of land where glacier melt contributes between 45 and 100%. And in the smaller circle, the darker blue, hectares of land where glacier melt contributes between 80 and 100%. So in Bolivia, we're talking about 61,000 hectares where glacier melt is contributing up to 100% of that irrigation, and 402,000 hectares where it contributes between 45 and 100. So really, really large quantities. And if we think about how that translates to domestic water use, each of these little I symbols to the right, each of these correspond to 1,000 people. And in black, those shows how many people are reliant on glacier melt for between 45 and 80% of their domestic water use. And in the red, that shows how many people are reliant on glacier melt for between 80 and 100%. So in Bolivia, there are over 500,000 people directly relying on glacier melt for at least half of their water use, where in Peru, more than half of the 360,000 people relying on glacier melt are very, very reliant on it for at least 80% of their water supply. And this is really important, as you can see on the figure on the right, left-hand side, because of variations in annual average rainfall, and a lot of the part of the coastal parts of South America are particularly dry and heavily reliant on this glacier melt. Another important consideration is something called peak water. This is a bit like a peak oil concept, but we apply it to water. And essentially, this tells us that glaciers melt in response to climate and create more and more meltwater as they do, so as they melt more in response to warming. But at some point in time, they reach this critical point that's called peak water, where the glacier has shrunk enough in response to climate that it can no longer produce enough melt to keep up that previous level of discharge. And this is really important because once regions reach this point, they really start to have to be concerned about their water resources and how they can manage them appropriately under a climate of reducing water resources downstream. Now, for some regions, estimates are that this period of peak water is already passed, and South America is one of the regions for which some of the glacial regions are already past that point. In Europe, in the Alps, we think that peak water is around about now in terms of the maximum amount of meltwater produced by the glaciers. So it's a bit of a boom and bust situation. We have lots of water now, but we can expect a lot less in the future. And in the Himalayas, partly due to the climate, but also due to the nature of the glaciers there, a lot of them are debris covered, for example, we predict that peak water is still to come. So perhaps we can learn lessons from other parts of the world and how they have dealt with the peak water issue to apply this to areas like the Himalayas down the line. So that's just an introduction to glacier contribution to downstream water resources. And before I come back to thinking more about the quantity issue, I want to focus really for the main part of the talk on this issue of contaminants in the cryosphere and impacts for water quality. So glaciers are obviously large bodies of ice and snow, and they store decades and hundreds and thousands of years worth of history in terms of atmospheric elements, in terms of pollen and all sorts of other things that are trapped in the layers of snow and ice in the glaciers. But they're also stores for anything else that fall onto their surface. So that could be elements from atmospheric deposition, that could come from accidents, so maybe helicopter or plane crashes in remote regions, incidents with snowmobiles or fuel drops in Antarctica, for example. So very much anthropogenic activity. And also anything that results from mass movements, so both landslide and avalanche activity. So it's not just the snow and ice that are stored in the glaciers, it's anything else that's available on their surface too. We sort of see that today, and particularly in the Alps, we're starting to see the emergence of some really quite ancient remains, in addition to remains from things like the Second World War that have now worked their way through the glacier and are melting out. But in addition to maybe the more harmless components of the glacier and what it stores, We also know that they can store things like persistent organic pollutants, heavy metals, hydrocarbons from some of these accidents that occur in these regions, but also some more rarely studied contaminants in the cryosphere. And what I'm focusing on in this talk are fallout radionuclides, so the product of weapons testing and nuclear incidents like Chernobyl. These are often used as tracers in the environment for other contaminants as well, but I'm actually focusing on them as contaminants themselves for the purposes of this talk. So because glaciers are retreating in response to climate change, there's a risk that those historical contaminants, so things like Chernobyl, you know, now from 35 years ago, and weapons testing era going back to the 50s and 60s, still stored in the ice, but through that increased melt in response to a warming climate, there's a risk of secondary release of contaminants into the downstream, what we call the proglacial environment, through both direct melting of the glacier and down wasting. So essentially the glacier becoming thinner as it melts and wastes away. So the aim that myself and my colleagues had when looking into this topic was trying to improve understanding of how fallout radionuclides are stored and released from glacier catchments across the global cryosphere. And also whether they're present at potentially harmful levels or not. Are they just diluted enough that they're no problem downstream? And this latter part is still something that we're very much looking to understand more. So to start off with, when I first got interested in this topic, I wanted to conduct a sort of proof of concept study first. And I chose to do it in Sweden in the Tarfala Valley, where I met Sergey a few years ago actually. And I chose this site because I know it well, and also because the Isfalls Glaciären catchment is very much a closed catchment. There are moraines that are marked in pink and green on the map on the top right there that bound the catchment. And so any meltwater coming from the glacier has to go through these two lakes that you can see on the map. So we know that meltwater is being trapped within that catchment that allows us to study the transport of sediments and contaminants really nicely in that region. So it's quite a small glacier, and it retreated quite rapidly between about 1916 and 1990. And since then, although the terminus, so the sort of downstream point of the glacier, has stayed roughly the same, it's thinned at a really quite rapid rate, leading to quite a steep ice surface and also a heavily crevassed ice surface, which makes it a little bit tricky to work on in terms of doing field research. So we focused on the southern lobe of the glacier terminus, which is the least steep part, to allow us to go and collect samples on the ice surface as well as in front of the glacier. So during our field campaign back in 2017, we collected Cryokinite. I'll tell you more about what that is. I suspect a lot of you wouldn't have heard of this before, but essentially it's a sediment from the ice surface. Collected samples from the moraines and the proglacial river outwash, and also retrieved a lake core for looking at chronology in the catchment as well. And all of these samples were taken back to the University of Plymouth, and we analysed them using gamma spectrometry, wavelength dispersive XRF, particle size analysis, and bulk stable isotope analysis as well, so we could look at organic content. So what's gamma spectrometry? This is not my area of specialism, but luckily I have lots of fantastic colleagues who do work closely in this, and I'm starting to learn more about it. But essentially gamma spectrometry quantifies radionuclides through analysis of those gamma rays that are emitted from individual samples. And we pop them in detectors. There's an example of this in the picture on the slide. We put a very small tube sample into this well detector that has a thick lead and copper shielding around it, and we analyse it in the detector for between 1 and 2 days to pick up even the smallest activity of some of the more rare radionuclides. And what that does is produce a spectrum of emitted gamma ray radiation that we can assign to different radionuclides in the environment. So what is Cryokinite then? I said I would explain it in a bit more detail. Essentially, Cryokinite is a sediment that is comprised, and it has to be comprised of both organic and inorganic material. So what makes it different from just normal rocky sediment is that it has this organic component. And we find this all over the world in the cryosphere. And it's amazingly organic, rich, and it's full of life. So because of that, we quite often think of cryokinite holes, the depressions in the ice where this dark material quite often pools, and when we think of them as being hotspots of biodiversity, and can be really quite unique. There are some estimates that suggest the amount of biodiversity on the surface of glaciers is bigger than what you would see in a lot of forests, for example. So really quite biodiverse environments, including things like tardigrades and other microbial life that we find there. But in addition to microbial life, it also contains obviously mineral matter. It does have components of the local geology, for example, black carbon that's been transported atmospherically, and also a range of contaminants from heavy metals to organic pollutants and other things. Cryokinite has been studied now for a couple of decades in detail, but largely from the perspective of the impact that it has on melting of the glacier surface. So it's a very, very dark black sediment. It's very fine, and for that reason, it doesn't protect the ice surface. It has the opposite effect. It changes the albedo considerably and enhances ice surface melting. So in places like the Greenland ice sheet, for example, cryokinite is very, very well studied from the perspective of its coverage to try and understand how that will impact and enhance how quickly the ice sheet is melting, particularly at the low elevation margins, such that we can actually see it from space as well. It really darkens the surface of the ice. And in the image on this slide on the left, you can see part of the glacier that's really quite dirty. It's like quite a different colour up above where I'm sampling, and that's covered by a thin layer of distributed cryokinite that causes more rapid melting in the environment. So in addition to all the microbial life, black carbon, mineral matter, what's also been shown relatively recently by Liz Bagshaw and others from a study in Antarctica was that cryokinite contains unusually high concentrations of carbon and nitrogen, and that it accumulates these in a much more high concentrations than other parts of the environment do. And it's theorized to thus be really quite an important component of the nutrient cycle. So just some photos now to just kind of give you a feel for what this environment looks like and the types of samples that we collected here. We focused on proglacial outwash, so that's that fine silty sediment that's transported downstream by glacier melt constantly, particularly in the summer in these latitudes. So we collected samples from proglacial outwash at both streams that exit the glacier at different points along the river, and collected samples from moraines, so those rocky boundaries of where the ice used to be, and in this case the moraines date to about 1910 when the glacier was at a much larger extent than it is today. Moraines are much more stable, and we don't expect the sediment to be particularly mobile in these locations, and actually often have a thin cover of vegetation, lichens and mosses, in addition to the rocky material too. We also took a lake core eventually. Initially we wanted to do this by boat and carried this surprisingly heavy rigid inflatable boat over a series of moraines to get into this lake in the hope that our gravity corer would work. But unfortunately these glacial sediments are so fine and so dense that we didn't have enough weight for the corer to work. It would just fall over once we put it into the water. So instead, to retrieve the core, took a little bit of creativity and a set of waders. You can't see it in the pictures, but it was actually lightly snowing this day as well. But we did manage to retrieve our core, 37 centimetres. I'm not going to talk about it today because I don't have time, but we have managed to reconstruct a really nice chronology of sediment transport from the glacier into this proglacial lake as well, using gamma spectrometry to help us date the different horizons in that lake core. So a bit about the results of this work now. What we found, if you can see in the yellow column in the table on the right, is that some of the numbers are considerably larger than the others. And that column that signifies our cryokinite samples, the samples from the ice surface, are often 2 orders of magnitude higher than those that we detected in samples from moraines and proglacial outwash sediments and the lake core. So for example, if we look at lead-210, which is a natural radionuclide, it's naturally occurring but deposited atmospherically, we had a maximum amount of 14,500 becquerels per kilo in terms of radioactive content, in comparison to about 73 in the moraines and 87 in proglacial outwash, so considerably larger in this ice surface sediment. Cesium-137, which is one of the sort of radionuclides that we associate closely with Chernobyl, for example, and other nuclear events. The maximum that we recorded in Cryokinite for this was 4,500 becquerels per kilo, and again, considerably larger than what we see in the downstream environment, where we have in the tens or low hundreds in terms of the radioactivity level there. What else we found, which was very interesting, was that the samples from the Cryokinite, but also some samples from proglacial outwash, were quite rich in beryllium-7. And this is a different type of radionuclide, and it doesn't have a very long life, basically. It's not present in the environment for very long once it's there. So we know that where we find beryllium-7, that these sediments must have been accumulated relatively recently, and they're quite mobile. So what this tells us is that those samples are interacting with meltwater frequently to pick up this content of beryllium-7. So just to illustrate this in a different way, the Cryokinite is not shown on these. Let me see if I can turn on my laser pointer. There we are. The Cryokinite isn't shown on these plots because it would dwarf the rest of the data. So this just shows samples from the central forefield of the glacier. So the land that's been exposed has been deglaciated many decades ago. 4 portions of the lake core going from the top down to the bottom, moraine samples in the skin to the right column, and the proglacial outwash in the furthest right. And what this shows is that cesium-137 is highest in the upper portions of the lake core, much higher than it is on other off-ice sediment sources, so the central forefield and then proglacial outwash. And this suggests that there might be some transport of radionuclide-enriched supraglacial, so ice surface sediments from the surface of the glacier down into the lake where it's accumulating. It was quite interesting to see that forefield in front of the glacier had such low levels of fallout radionuclides, despite the fact that it had been exposed to the air long before the weapons testing in Chernobyl era. So it was interesting to see that the sediments there were not accumulating radionuclides at anywhere near the same level as those sediments that come into contact with water more frequently. And we also, as I said before, really only found beryllium-7 in samples where meltwater flow is recent and active. So the proglacial outwash, like we see here, the upper lake core are not shown on this figure, the Cryokinite samples from the ice surface too. So these plots show the spatial variability in different radionuclides and also in the carbon and nitrogen content of the Cryokinite samples. We took these in 2 transects across the glacier to see if elevation or aspect made any difference to the levels that we see. And what we've noticed is that, particularly if we look here and the levels of lead-210 and beryllium-7 in these samples in the northernmost part of the ice, this corresponds to levels of carbon and nitrogen in the samples that are higher than the other samples, and that points towards organic content being really important for accumulation of radionuclides as well. And we think that makes sense because this side of the glacier is the sunniest side. It's the side that experiences the most shortwave radiation. It also experiences the most melt. So there's more meltwater being produced, and thus any sediment on the surface there is likely to come into contact with more meltwater than the more shady side of the glacier where we have much lower values. So that really points towards the importance of the level of organic content in the samples in terms of controlling how much radioactivity each of the samples contains. So why do fallout radionuclides accumulate in this ice surface sediment? As I said, Cryokinite in the past has been shown to be very efficient at accumulating carbon and nitrogen and phosphorus as well. But our research really shows that the same is true, not just for fallout radionuclides, but we also looked at a range of other major and minor elements and found that a number of those were really quite elevated in our samples too. And we think that because these fallout radionuclides are old, they're historical contaminants that we can trace back to things like Chernobyl and weapons tests. They're stored and trapped inside the ice and snow, have recently been melted out, and as they're released and transported downstream, that meltwater interacts with this organic rich sediment that accumulates fallout radionuclides as it's transported downstream. So we think there's probably an element of bioaccumulation here, given the link between the organic content and the radioactivity levels, fed by a supply of meltwater that keeps that accumulating and topped up. There is a competing theory by a group in Austria that suggested that radionuclides build up in cryokinite directly over long periods of time. So assuming that these cryokinite holes sit as they are for many years and accumulate more and more radionuclides as they sit here. But these holes are filled with water, and the sediment, I can assure you as you go to collect it, is quite tricky. It moves very, very easily because it's very, very fine, so it's disturbed very easily. And when we have large melt events, when there's a lot of meltwater produced, we know now that cryokinite moves quite freely across the surface of the glacier. So this theory is unlikely to be true. And because our samples contain such high levels of beryllium-7, that further suggests that this is a young and mobile sediment. So that was a case study that we did in Sweden, really, when we first got interested in this topic, but which was really interesting in itself and really fun to do. But what we're really interested in is thinking about what that means from a global perspective in terms of downstream water quality in glacial catchments, particularly land terminating rather than ocean terminating glaciers. So I've teamed up with a number of researchers at other universities around the world to pull together data that we have on cryokinite from 22 different glaciers or areas of ice sheets such as Greenland. And this spans mountain glaciers, ice caps, ice sheets. We have Antarctica in our sample set as well, and a whole range of different climatological regimes from different latitudes across the globe. And in addition to cryokinite samples, we also have some sites with additional proglacial soils and sediment, so we can actually look at that sediment transport and the differences in accumulation as we move downstream through the proglacial system. So we have sites from South America, North America, Greenland, a few sites across Europe and Antarctica, and also in the future we have future field campaigns planned for Peru, and also way up in the northeast of Greenland, hopefully next summer. So just to sort of flag up a few of the people that I work with on this, we have Will Blake, who I work with at the University of Plymouth. He's my main colleague and runs the consolidated radioisotope facility here. Giovanni Baccalo, who's in Milan in Italy. Edita Lokas, who works at the Institute of Nuclear Physics in Poland, and Phil Owens, who's over in UNBC in Canada. So we've analysed quite a large number of samples across our different sites, up to 102 samples, so lots and lots of different cryokinite samples there. Some of the most recent samples we've had are from the Himalayas, from the Ladakh region, and from the Chilean Andes. And as I said, there are more to come, including our field trip to northeast Greenland that should have happened this summer, but obviously with the coronavirus situation, we weren't able to. So we'll be doing that next year. And also I have collaborators in Peru. This is Wilmer, who has been collecting cryokinite for me while I'm unable to get there myself. So it's fantastic to have such a supportive network of researchers helping with this as well. So some results from the global database that we've been putting together looking at these radionuclides. If we look at lead-210 first, so this is a natural radionuclide, we see that the levels are highest over northern Sweden, so actually from the sites that I've spoken about already, but also the sites that Phil Owens has looked at in Canada too. The highest average value over 9,000 becquerels per kilo, the highest single value of 14,500, and this is really, really high. It's really quite considerably higher than lots of other types of environmental matrices that are typically analysed for radionuclides. Coming into the artificial radionuclides or fallout radionuclides here, cesium-137, that, as I said before, a lot of this was deposited after Chernobyl. And it's particularly interesting in places like Sweden, where I've done work, because there was such a legacy of impact following that on reindeer meat and also wild boar. But even today, the Swedish government recently had a sort of sampling campaign where hunters were able to submit boar meat to be tested, and even just in the past couple of years, some wild boar meat in Sweden contains 10 times more than the legal limit of cesium in the meat, which means it's not able to be sold and used for consumption. So it is still important that this is in the environment. It has a half-life of 30 years, so it has reduced now by half since the deposition during Chernobyl, but there's still large quantities in the environment. So the sites I showed you from Sweden, the highest average value in terms of averaging the 14 Cryokinite samples was just over 3,000, but actually we have an incredible level of 13,500 becquerels per kilo of cesium-137 from a glacier in the Swiss Alps. And that, we think, is one of the highest levels of radionuclides from cesium recorded outside of nuclear exclusion zones. So it's very, very high. And just to compare a little bit further in terms of regional variation, we have these really, really high values, again, European Alps, also in the Caucasus and Fennoscandia. But if we look at Iceland, it's a bit of an anomaly here, because the levels are they're still high comparatively compared to other types of landscape, but much, much lower than the other sites we've looked at. I'm still doing analysis of these samples now to look at the organic content, but I theorise that this has something to do with the volcanic activity in Iceland and the impact that has on the organic content of the sediment there. And then finally coming to americium, which is another product of nuclear testing and nuclear energy, and it's a decay product of plutonium, and it has which has a half-life of 14 years. But americium, once that's produced through that decay, it has a half-life of 432 years, so it hangs around in the environment for a very long time. Now, while the absolute values in terms of becquerels per kilo for these are much, much lower, it's important to note that americium-241 is a strong alpha emitter, and it's quite soluble as well. So in terms of if it's consumed, if it's taken up in the food chain, it can be particularly harmful. So key results sort of emerging from those studies are that certainly the fallout radionuclides are widespread across the global cryosphere, and we've found elevated levels in every single cryokinite sample that we've analysed, regardless of where that's been sampled. Cryokinite itself has exceptionally high levels of both natural and artificial radionuclides, and well above those that have been found in the past and things like lichens and mosses that are known to be efficient accumulators of radionuclides because of their reliance on atmospheric deposition. And also, we've found some of the highest levels recorded outside of nuclear exclusion zones in terms of levels found in the natural environment, which really highlights quite how unique and special cryokinite seems to be in its ability to accumulate anthropogenic contaminants within the sediment. So what are the impacts and potential applications of this? Obviously, there are concerns about this secondary contamination, so actually melt out of things like Chernobyl, fallout from decades ago, but occurring again now, and thinking about what impacts that might have downstream, particularly for aquatic life. But what we don't know is how much mass of fallout radionuclides there is. So while we know the levels are very, very high, this material tends to be quite distributed and quite isolated in terms of where it's found on the glacier surface. So we need to do a much more in-depth study of how much material there is, so we can really assess whether there is any downstream impact at all. It's very much unknown. There are also ideas that we could maybe use Cryokinite as a biomonitor for fallout radionuclides in the remote parts of the world where actually there just isn't very much vegetation, for example. Lichens and mosses tend to be used in other parts of the world as a monitor for what levels of radionuclides we have currently. But places like Greenland and Antarctica, where vegetation is limited over large areas, perhaps Cryokinite could offer a way for us to monitor that there. And I think in addition to expanding our database further, just trying to collect as much information we can on this, we'd like to look at things like sequential extraction and looking at how this is then taken up from Cryokinite into flora and fauna as well, again, to think about assessing any potential harm it might cause. So very quickly, for the last 10 minutes, I'm not going to go into this in as much detail, but I just want to talk a little bit more about glaciers and how they interact with that water, food and energy security nexus. So this figure here shows really nicely, this is from the UN, shows really nicely this interlinkage between energy, food and water, and right at the centre of that we have people, ecosystems and landscapes. We spoke before about the pressures on that nexus from economic growth and population change, for example. But I would very much highlight here that I think to really tackle some of these issues, we have to take a very much interdisciplinary approach to our research, and also including the people that this impacts in terms of co-production of knowledge and actually creating our research alongside the stakeholders that this ultimately impacts. So how does this impact glaciers in the Peruvian Andes? So this is my other research site at the moment. It's a project that I've had funded for the past almost 2 years now, and will have for another couple of years, looking at downstream impacts of glacier change on water quantity and quality in the Andes. So about 10 million people here rely on glacier meltwater, which is a huge number. And in the Rio Santa catchment, where we're focusing, about 10 to 20% of annual river discharge comes directly from glacier meltwater. But during periods of drought, that's up to 90%. So it can be considerable. And in Peru, Peru is fantastic from the perspective of having such a large proportion of their energy from hydropower, about 50%. But that means that reduction in how much meltwater is available is also problematic for generation of energy here. And unfortunately, the Cordillera Blanca that contains these glaciers, it's the most glaciated tropical mountain range on Earth, but it has decreased in terms of ice covered area by 35% in the last 40 years. So our project really tries to look at the Peruvian Andes and downstream impacts of glacier melt from a nexus perspective, and trying to build a decision support framework so that stakeholders can choose how they want to mitigate and adapt to these pressures on the nexus, particularly looking ahead to the post-peak water period where those resources will become less and less plentiful. But there are some pressures on the nexus that are perhaps slightly different in some other regions in this part of the world. I won't go through all of them here, but certainly we can include geopolitical conflict and corruption. In Peru, it's obviously quite unstable at the moment in terms of politics, with changes in leadership again there. But in addition to geopolitical issues, there are also a lot of natural pressures on the nexus, things like flooding from glacier lake outburst floods, earthquake activity and landslides. So lots of additional pressures that can cause issues in this region. So there are sort of 4 main work packages, and I'm not going to go into any of the results of our project now because we're still very much in the middle of it, and I've obviously been a little bit delayed and disrupted over the past 9 months or so because of the COVID situation. But the first part of our project is very much looking at water budget development. So thinking about glacier contribution, meteorological scale, event variability, and trying to apportion how much of the water downstream in the Rio Santa catchment can be attributed to glaciers, precipitation, snowmelt, and groundwater as well. We're also looking at basin connectivity in terms of sediment transport in particular, and how that might respond to a changing climate. And to do that, one of my students, Jess Kitch, is looking at sediment fingerprinting, and also looking at hydrological SWOT modelling to look at sediment transport, and also looking at future scenarios for what would happen. What happens if you remove the glaciers? What happens if you change this type of land use to something else? What impact would that have on sediment and water fluxes downstream? So we are using a sediment source apportionment model to do this, to try and look at the sources of sediment in the catchment and how important the glaciers are in generating and transporting sediment in the upper reaches too. So this is based on work by Will Blake that he's applied to a range of different catchments elsewhere. And we sort of associate this as being a little bit like Cluedo. So sediment fingerprinting is really trying to understand what's happening in a catchment. So if we have two tributaries in our catchment, we have a red tributary and a blue one, but downstream there might be a sediment problem. Maybe a hydropower dam is suffering from siltation, for example. We want to know where that sediment's coming from. So if it's red, that's straightforward. We know it comes from the red sub-basin, from Miss Scarlet, if you're a Cluedo player. If that sediment is blue, if that's a fingerprint it has, we know where that's come from as well. But what happens if it's purple? What happens if it's a mixture? It's not a purple sediment, it's not Professor Plum. It must be a mixture, and we have to use these unmixing models to try and unravel what we call these complex fingerprints downstream. So that's something that we're applying to the Rio Santa catchment too, to look at sediment apportionment. And the other thing that we're looking at from a physical science perspective is the natural and anthropogenic contaminant fluxes in the catchment. I've included this quite striking image here that shows very, very iron-rich water in a downstream river. Sometimes in this region, this is associated with mining activities, and quite often it's certainly blamed on mining companies, but the reality is that actually the local bedrock in this region can sometimes be very, very rich in heavy metals, and sometimes just glacial erosion and downstream transport is enough to turn the rivers into this quite striking colour, and even to the extent that it can result in pH being significantly reduced to being really quite acidic. But that is very much a natural process for the most part. So natural is almost as much of a challenge here as some of the anthropogenic pressures. So we're interested in fallout radionuclides, as we have been in other areas, but also on things like heavy metals and microplastics that we might find in these environments too. So it's quite a wide-ranging project, and there are lots and lots of collaborators, both from the UK and multiple institutions in Peru that we're working on together in this project over the next couple of years. And the final part, just before I wrap up, is just to really highlight the importance of stakeholder engagement for these types of projects too. Ultimately, in this region, we know that locals have a bit of research fatigue, because so many projects have studied this part of the Peruvian Andes. There are, I think, well over 150 hydrological papers alone looking at the Rio Santa. But this very rarely filters down to policy change, or filters back to the people that have contributed maybe local opinion. And we know that this is becoming a frustration in the region. So this final work package is really core to our project, and for that reason we're working with social scientists to help us understand what the priorities of the local people are, how they feel about changes to the environment there, and thus hopefully mean that there's more local buy-in to mitigation strategies in the future too. And we're doing that through trialling a new payment for ecosystem service model in the region that's very much still in development as well. And in addition to this, we're also hoping to contribute to outreach and education through our project as well, and I've done this recently by creating a tool called Glacier Map. You can take part yourself. This is for anyone to use, everything from school kids all the way up to retired people, anyone who wants to join in. The website is peruglaciers.org. And this allows people to map glacier change from Landsat satellite imagery of the Cordillera Blanca in Peru. So we have essentially crowdsourcing, or a citizen science project, that helps us to understand how rapidly the glaciers are changing there, and in doing so help to distribute knowledge and improve education around glacier change in the region. So to wrap up, 3 take-home messages. The first is that I think that glacier-fed water security is absolutely crucial for the water, food and energy security nexus, and that's particularly true for regions like the Andes and the Himalayas. Take-home message 2 is that water quality has to be considered at least as much as water quantity. Particularly because we know that glaciers are nothing more than temporary stores for legacy historical contaminants. So we know that whatever is stored in those now will make its way downstream at some point. The glaciers are very rarely growing. The vast majority of glaciers on Earth are doing the opposite to that. So we really have to consider water quality in glacier-fed regions too. And the third take-home message is that we also have to consider the socio-environmental impacts and stakeholder perspectives when we're doing these types of research projects, in order to really try and make a difference and come up with ways to mitigate changes to water availability and to water quality too. So with that, I will wrap up, and I think I'm on time, which is amazing. So thank you very much for listening.
Yeah, thank you very much, Caroline, for such a multiple aspects lecture. We learned a lot from this, and we have a couple of questions for you from our participants. And the first question is from a researcher from, I don't know how to pronounce it right, Institute of I don't know, sorry, I'm not sure that I know this abbreviation. So this researcher is from Moscow, and he'd like to know what sort of bacteria do you observe in glacier water, and where do bacteria usually concentrate in organic-rich cryokinite?
That's a really good question, and I do not have the answer for it. I'm not a microbiologist at all. There are some fantastic papers out there that you could look up if you're interested. You can look at papers by a researcher called Arwen Edwards, who's at Aberystwyth University. There's also, and I'm not going to be able to pronounce his name, Krzysztof Zarowska. I'm not sure exactly what his name is, but he looks at things like tardigrades and other biological material in cryokinite as well. But yeah, it's not my field of expertise, I'm afraid.
Right. Okay. Okay, thank you very much. And one more question from me. So you said that there is no studies about relations between radionuclides concentration in ice and in glaciers and rivers downstream. Is it real truth? I mean, a lot of people supplied with water from glaciers and they drink it, but how much do we know about, origin of this water, and yeah, how it could impact our health, for example, not our, but people in Sweden and other countries? Yeah,
there really is very little information as far as I'm aware. So in terms of studies on cryokinite, there are now a number looking at individual glacier sites, and my colleagues and I are hoping to publish our work soon on the global perspective as well. Fallout radionuclides and gamma spectrometry have been used in the past to date ice cores, for example. So people have done studies taking portable spectrometers into the field to try and get horizon dates in ice cores, for example. But to my knowledge, that really hasn't been translated into how much is being transported downstream. So I think there's only 1 or 2 studies at the moment that actually have published data from both the glacier and downstream sediments. So yeah, very, very little knowledge. If there's anything, I know that some work has been done actually from some researchers in Russia. Someone sent me the best translation they could manage. So sometimes you find that there are other studies that have been done elsewhere that maybe aren't in the the English written literature that I don't know about. So if anyone does know of any, I'm really interested to hear about, because I'm trying to gather as much information as I can about this.
Okay, thanks. And one more question about bacteria. Pankaj Kumar would like to know what harm these glacial bacteria cause to human. Are they really important? Yeah.
I don't know again about the sort of bacteria within the cryokinite, but in terms of the radionuclides, in small quantities, we all consume radionuclides, you know, whether they're fallout radionuclides or cosmogenic, you know, we're constantly being bombarded by cosmogenic radionuclides, and on the whole, they're not harmful. However, it's ingestion of some of these things that can become a problem. So if you eat reindeer meat that's contaminated by it, for example, or fish, or drink water that has a particularly high concentration, that's where the problem can lie. But we just don't know yet, because we don't know what the mass of cryokinite is and how that translates in terms of downstream dilution. It's just, we don't know essentially yet if that's actually harmful. But what I wouldn't suggest, I don't think I would think again before I drink water from the surface of a glacier, which I've always done on field work. I always, you know, you don't carry your water bottle, you take it up there with you and fill it up with a stream. And I have to say, I would think twice about doing that again now.
Yeah, the same. When you study water quality, you always think
Yeah.
about yeah. Gabe, would you like to ask something? Do you have some questions?
No.
So I think
say thank you, Caroline.
No, you're welcome. Thanks very much for having me.
Yeah, thank